Welcome to Radicals. Today we are going to talk about simplifying radicals into simple radical form. Before we dive into simplifying radicals, we need to do a little bit of background information on what is a radical or what is a root. Currently we've been working with simplifying exponents. So what we've been able to do so far is take a value, raise it to a power like 2 to the third, and get a value that's bigger than what we're starting with. That's doing a power and getting a new value. Doing a radical or doing a root is actually the reverse process of that. So you're starting with a bigger value and then you're finding the root from which this value here came from when you do a power. Here is a quick list of values that come from being squared, or these are called square numbers. These are very popular values from which we find the root of where the value comes from. So this would be called finding the square root, in this case 4. 25 is a squared value. When we take the square root of it, we find 5, its root. Same thing with 81 as a square value, square root it, or do the radical of it, and we get 9 as its root. Here are more examples of various bases going to different powers. So we've got 5 going to the power 4, getting this big value here. So we can reverse that process, start with the big value, take the 4th root of it, notice that matches the power that the 5 was raised to, and then we get back to the root of 5. Another example, we've got 4 to the power of 6 gives us this new big value here. So if you take the 6th root of 4096, you'll get back to the root of 4. 2 to the 8th equals 256. If you take the 8th root of 256, you'll get back to the root of 2. A little bit of terminology here. This symbol here is called the radical symbol or the rooting symbol. We've got all kinds of roots, so pretty much for every, exactly for every power that exists, there is a root that is its inverse, that inverses the process. So here are some examples. Specific parts of a root really are 3 parts. You have the radical symbol itself. You've got the little value that designates the matching power to which the root belongs to, or inverses. That's called the index. And then you have the value underneath the root. That's called the radicand. Is it possible to find roots for all radicand values? So here's an example where we're looking, or we're being asked to find the square root of -16. We're asked to think about what base multiplies itself and gives us -16. So we know that 4 times 4 equals +16. We know -4 times -4 equals +16. But is there a value that multiplies itself to get us a negative value? And so here the answer is no, because there's no real root that will get us a squared value to equal a -16. Here's another similar question. This time it's asking us to find the cube root of a value to equal -27. So it's basically saying, what is this magic x that multiplies itself 3 times to equal -27? Is there such a thing? Right? So we can try 3 times 3 times 3. 3 times 3 is 9, times 3 is a +27. What happens if 3 is negative? We get a +9 times a -3. We do get a negative value, so we get -27. So here we do have an answer the cube root of negative 27 is negative 3. So here it is possible to find a root. So here we just observed two different situations. We were able to find a root for the cube root, which has an odd value index. The 3 for the cube root is odd. If the radicand's negative, we can find a root. However, if our index is even, like the square root, which indicates, by the way, that the little index there is 2 because it's the opposite of a square root, the radicand is negative, we won't be able to find roots. So index is odd, you can find a root. If it's even, there's no real root. Now it's time to get to business. Our goal today is to simplify our radicals. So we're trying to find the root of the value. If it happens to be a perfect square, perfect cube, perfect power 4, etc., we can actually look it up and get an answer. We could actually plug it in the calculator and it comes out to a whole number. However, if it's not a perfect square value and we're asked to take the square root, we're going to get a decimal value. We are not trying to get a decimal value here, but we're going to want to simplify the radical to get as many perfect square values or perfect cubic values out of the radical. Your answer will probably still have a radical. So to illustrate what I'm talking about here, we're going to work with this example, the square root of 48. So if you take the calculator, you'll find that 48 is not a perfect square because you don't get a whole number. So when you think about the value of 48, which comes from something getting squared, it's actually a value that's between the square root of 36, which we know is 6, and the next perfect square is 49, which has a root of 7. So it's a decimal value somewhere between 6 and 7. But right now, we're not worried about getting decimal values since those are really estimate values. They're not as accurate as leaving values in radical form. We're going to follow this process here, which is called simple radical form. So please make sure you jot this down. We start with our radicand, 48. And we think about, is there a square number that divides into 48? When you're thinking about square numbers, you're hopefully picturing in your mind 1, 4, 9, 16, 25, and so on. So we're asked which one of these values here divides into 48. You're looking for the largest possible square number that divides into 48. That would be the number 16. It's a perfect square. It divides into 48. It goes in 48 3 times. 16 times 3. So now that you've recognized what's going on here, you've got 48 broken up into a product of 16 times 3. We're basically just writing 48 in a different way. We're writing it into factors. So 16 times 3, and the reason again we picked this factor pair is because 16 is a perfect square. Now that we've rewritten 48 into 16 times 3, we can actually break up this into square root of 16 times square root of 3. And then that takes us to the next step, which is find the root of the perfect square. And the perfect square here that we're referring to is this guy right there. It has a root of 4. So we basically take square root of the perfect square, which is 4. And then the second value is stuck under the radicand because it's not a perfect square. It stays as a radicand under the radical. And so now this is our answer. We've rewritten square root of 48 into a simpler radical, which involved taking out the largest square number that divides in 48. Here is another example to illustrate the process. Simplify 3 square root of 50. So we're asked to take the square root of 50, and whatever it comes out to be, multiply to 3. That's what is really meant here with this outsider value. So when you're evaluating the square root of 50, you soon discover it's not a perfect square. It's actually in between the square root of 49 and the next square, I believe, is 64 from 8 times 8. So 50 is certainly not a perfect square. So then you ask yourself, all right, with the square root of 50, what's a perfect square value that can divide in there, hopefully the largest square value? 4 does not go into 50. 9 does not go into 50. 16 does not, but 25 does. So this can be written as square root of 25 times 2, because 25 goes in 50 twice, and 25 is a perfect square. So we're picking a specific factor pair here, again with first value being the perfect square. At this point, we can break up this into two radicals multiplying. That's just something that we can do with radicals. Separate them to two different radicands. Take the square root of 25, which is 5. The square root of 2 stays in the box because it is not a perfect square, and it's as simplified as possible. And then the very last step is to take this here and go back to the beginning. Is there more to do here? If you recall, I mentioned that what was happening here is 3 was multiplying to whatever this simplifies to. So that's indeed what is happening, is 3 is multiplying to this 5 square root of 2. And since these two values are outside the radical, they certainly can multiply together to give us 15 radical 2 in simple radical form. We'll do more examples in class.